Dear students, hope you watched my previous sessions on digital communication, and this is the third class online. So in this class, I would like to introduce you to the concept of sampling. We'll discuss sampling theorem, what is a continuous time and discrete time signal, what is Nyquist rate, and what is aliasing. And for your information, so these topics are actually not included in the syllabus. It's not included in the syllabus, but for you to understand the concept of digital communication, you should be knowing what is sampling, what is aliasing, what is sampling theorem, etc. So we will discuss what is a discrete time and a continuous time signal first. So you know that due to the advancements of digital electronic devices, you know that all these analog electronic systems are getting replaced by its digital equivalent. So, and almost all these practical or real life signals are analog, is it not? As we discussed in the last sessions, you know, all this practical information, for example, speech, temperature, whatever be, is analog in nature. So before the process of processing or transmission, these signals must be converted into digital. Okay, so I will explain what is a continuous time signal right now. So this figure, so I can tell you, this is a continuous time and continuous amplitude signal. Continuous time in the sense the signal is completely defined for the entire time duration. For every instant, the signal amplitude is defined and its amplitude is also continuous. Okay, so this is a continuous time, continuous amplitude signal. For example, our sine wave, a triangular wave, all these are continuous time signals. Next, I will show you what is a discrete time, continuous amplitude signal. Discrete. The term discrete means it is not continuous. The time is not continuous. Okay. So here the time is not continuous. The signal amplitude is defined only at certain time slots. Is it not? See, the signal is defined here. It is defined at this time instant. Likewise, these signal amplitudes are defined only at certain time slots. So this is a discrete time continuous amplitude signal. Okay. The third type of waveform is a continuous time but discrete amplitude signal. Okay. So we can see the difference. The signal is defined for the entire time duration from 0 to t. So the time period is continuous, but the amplitude is not continuous. It has certain discrete levels. Just like the first waveform, it's not flowing continuously. This is having discrete amplitude levels. And the last type, that is a perfect digital signal, is a discrete time, discrete amplitude signal. That is, it is discrete in both time and amplitude. So discrete time means it is defined only at certain time slots. Okay, it's not completely defined. Only at certain time slots the signal is defined, and the amplitude is also not continuous. The amplitude is also discrete. Okay, so it is defined only at certain time intervals. For example, for time t equal to 0, the amplitude is 1. For time t equal to 1, the amplitude is 2. Okay, and in between this 0 and t, for this time duration, the signal amplitude is not defined. Okay, if you compare this with the first one, from 0 to t, the signal is having infinite number of values. Is it not? The signal is having an infinite number of amplitude levels from 0 to t. Now tell me, transmission of which requires more bandwidth, that is the first case or the last one? You know that for transmitting the first signal, we have to transmit the entire voltage variations. Is it not? Is it not? But in this case, only certain amplitude levels need to be transmitted. Okay. Now, so I hope you understood what is a continuous time signal and what is a discrete signal. Okay, a continuous signal is having continuous time or continuous amplitude, and a discrete time, the time is discrete and the amplitude can also be discrete. So before converting the signal into a digital sequence, first it is converted into a discrete time signal. And for this, we have a mathematical tool called as sampling theorem. Okay, so it is a mathematical tool for converting a continuous time signal into a discrete time signal. Okay, so instead of transmitting the complete signal, only the samples are transmitted after sampling. Okay, and there are two important points. There should be sufficient number of samples taken, and it should be possible to recover or reconstruct the original signal from these samples. I repeat, for successfully transmitting and receiving an information from the original signal, sufficient number of samples must be taken, and the second is we should be able to recover or reconstruct the original information from these samples. Okay, so this is very important. There should be sufficient samples and we should be able to recover the original information as it is transmitted. So sampling is the process of converting continuous time to a discrete time signal, and this is the definition of sampling theorem. Sampling theorem states that a continuous time signal may be completely represented in its samples and recovered back if the sampling frequency is Fs greater than or equal to Fm. Okay, so sampling theorem, there are two important aspects. That is, if any signal, any continuous time signal can be represented using its samples. So that is the first point. Okay, any continuous time signal, whether it be a sine wave or a triangular wave, whatever be, or a speech signal or an audio information, a music, whatever be, this signal can be completely represented by its samples taken at regular intervals. Okay, it can be completely represented by using the samples. And from this samples, the signal can be converted back into its original information. Okay, so if you are converting a speech signal into its discrete time, some samples will be taken, and after transmission at the receiver end, from these samples, the information is converted back into its original form. Okay, so here we represent Fs as the sampling frequency and Fm as the maximum frequency in the information. Okay, so we have two concerns, two important parameters. Fs is nothing but the sampling frequency, and Fm the maximum frequency in the input message signal. Okay, and if the minimum sampling rate Fs is equal to twice Fm samples per second, then this rate is called as Nyquist rate. Okay, repeat. So if you are taking samples at a rate 2 Fm, the rate is called as Nyquist sampling rate. Okay. Now the significance of sampling rate. If I will explain this with the help of a diagram. So this represents the significance of selecting the correct sampling frequency. Suppose I am transmitting a frequency of 5 kHz. For proper transmission and reception, the sampling frequency must be at least equal to twice time 5 kHz or 2 times 5 kHz, that is 10 kilohertz. Okay, so whatever be the maximum frequency I am transmitting, the twice of that maximum frequency should be the sampling frequency. So in this figure, look at the second diagram where the frequency, the sampling frequency is equal to twice Fm. Okay, this is equal to twice Fm. Fs is the sampling frequency, Fm is the maximum frequency contained in the message. So the successive frequency cycles will not overlap. Okay, they are just touching but will not overlap. But if it is greater than twice Fm, that is, if Fs, the sampling frequency, is greater than twice Fm, we call this as oversampling, that is, more samples are taken. Okay, more samples are taken. So the frequency spectrum of such a waveform will be like this. Okay, and Fs is less than twice Fm. We call this condition as undersampling. And now from the figure itself, if the samples are taken at a rate less than twice Fm, the successive cycles will overlap each other. We can see here these signals are overlapping in these areas. So while receiving such a signal, it won't be able to demodulate or reconstruct the messages in these frequencies or in these time slots. I hope you understood. So this is the significance of sampling theorem. The sampling frequency should be taken very carefully. If it is undersampling, the frequency components will overlap. Okay, and this overlapping of nearest cycles is called as aliasing. ALIASING, aliasing. Okay, so this is an error in digital communication system. The cycles should not overlap each other. For that, the perfect sampling frequency is Fs equal to twice Fm. Okay, so if this is the frequency response of such a sampled signal, at the receiver end, the original information can be reconstructed as such. Okay, but in the first case, if more number of samples are taken or oversampled, it requires more wider bandwidth to transmit such a signal. Next is methods of sampling. Okay, methods of sampling, we can see there are three different methods of sampling: ideal sampling, natural sampling, and flat top sampling. Ideal, natural, and flat top. So from the figure itself, we can see the difference. In ideal sampling, only some amplitude levels are transmitted. So this is the original wave, a continuous wave, and only these amplitude levels are transmitted and processed. In natural sampling, instead of taking a particular amplitude level, a range of amplitude levels are transmitted. Okay, for this time duration, these amplitude levels are being processed and transmitted, and in this time slot, no signal is transmitted. Again, for the next time's duration, this is the amplitude variation which is getting transmitted. Okay, so the signal is defined only at certain time intervals. Okay, in this time duration, this is the amplitude being transmitted. And the next method of sampling is flat top sampling. In flat top sampling, rather than transmitting a discrete time continuous amplitude signal, so we can see the natural sampling is an example of discrete time continuous amplitude signal. What do you mean by discrete time? Discrete in the sense the amplitude is defined only at certain time slots, but the amplitude is varying continuously. Okay, so here in flat top sampling, the amplitude levels are defined at certain time slots, and these amplitude levels are flat or constant. Okay, in the previous case, the amplitude level is varying, but here the amplitude level is not varying, it is remaining a constant. Okay, so I hope you understood what is sampling, what is Nyquist rate, the significance of selecting the sampling frequency. And now let me ask you one question. See, what could be the advantage of transmitting such sampled version of a signal? So instead of transmitting the complete wave, if you are transmitting only some amplitude levels, what could be the advantage of such a system? Just find out an answer for this question and send me the answers for getting attendance.